mind taking a seat, and obviously we'll get to the first way away. Okay, thank you very much. Got a gentleman in reception there. I've got something in the headlight. The Rover's going to get an
The engine bay of a modern car can look a bit intimidating. Where do you start when trying to find a fault? Where do you look? And what should you do? As new electronic systems have been developed, the importance of following a logical fault diagnosis procedure has become even more critical. Sophisticated electronics are now so common on today's cars that almost every problem you encounter will involve checking an electrical circuit. The Rover Sterling's electronic systems at first look a bit daunting, but the only difference between the Sterling and other cars you've been working with is the amount of electrical circuits you'll encounter. Once you isolate each individual circuit, fault diagnosis becomes quite straightforward. So in this program, we're going to look at the Rover 800 electrics and see how the principles of fault diagnosis can be applied to enable you to find any fault on the car. I'll go through the troubleshooting process on 3 of the Rover's circuits: the headlights, the central door locking, and the windscreen wipers. Austin Rover have already produced 2 programs on car electrics. Remember these 2 Service Insight video programs: Electrics and Electronics and Electric and Electronic Systems Diagnosis. The first took you through basic electrical principles, explaining common terminology and measurements. The second took a more in-depth look at electrical fault diagnosis with the use of a multimeter and fast-check testers. Now, it's essential that you watch these videos to understand the principles that we'll cover in this program. Right. Now, in the Systems Diagnosis program, you'll remember that the principles of fault diagnosis were broken down into 6 logical steps. These form 3 main areas: collecting and analysing information about the fault, isolating the particular area of the circuit where the fault is likely to be, and then actually pinpointing the fault itself. But before we start any diagnosis, let's take a look at the new style fault diagnosis material and information contained in the booklet that accompanies this video. Now, this reflects a completely new approach to wiring diagram layout. Each individual circuit is covered separately rather than in one big diagram. Details such as whether connectors are male or female and which areas of the circuit have sealed joints can all be easily identified. Familiarise yourself with this style of literature because you'll be seeing a lot more of it in the future. The booklet is split up into 2 sections. The first contains information on fuses, harness layouts and earth point locations, together with the procedure of testing both the yellow and green relays found on the Rover 800. The second part is divided into 3 sections, one for each of the circuits we'll be testing in the program. Each section contains a circuit diagram, plus a brief description of how the system works, and a guide to fault diagnosis. The wire colour coding used on the Rover 800 is the same as that used on previous models with British-built harnesses. For example, blue for headlights and brown for the battery supply. Don't forget, there's a reference list provided in the booklet with this video. Now, if we take a look at the main harness with no sub-harnesses or components attached, you can see that it has an H-shaped layout. This shape was developed so the harness lies as close as possible to the components it serves, reducing the amount of potentially troublesome connections. The harness is protected behind the dash and down each side with plastic trunking. Along this trunking there are breakout points to serve the various components. These 2, for instance, are for the driver's seat. There's a harness layout diagram in the repair manual which shows all the breakout positions. Knowing the harness layout will be a tremendous help to you when diagnosing electrical faults. It will enable you to plan ahead and find the easiest and most effective starting point to plan your tests. This is one of the Rover 800's 2 fuse boxes. It contains 6 fusible links, 13 normal type fuses, and either 5 or 6 relays, depending on the model. An illustration in the repair manual shows the lettered identification of the fuses and the function of the relays. The other fuse box is behind this dummy glove box panel. Fuses here are numbered 1 to 19. Behind this fuse box is the relay tower. On this you'll find, among others, the headlamp changeover unit, which is the black one, the headlamp delay unit, which is red, and the windscreen wiper relay, which is green. Again, the repair manual identifies the function of each relay. So why are so many relays used on modern cars? The answer is packaging, the ability to provide a fascia that is ergonomically designed with all the features that customers expect in such a small space. Take this simple fog lamp circuit, for example. This is the size of switch you need to carry all the current flowing around the circuit. It has to be this big to house the large contacts that a high current circuit needs. The wires to and from the switch also need to be large to carry the current. But using relays enables us to use small switches on high current circuits and thin wires to and from these switches. Now what I'll do on this fog lamp circuit is place a yellow relay across these 2 terminals, 30 and 87. This leaves terminals 85 and 86 spare. It's across these 2 that I'll put the switching circuit, a live feed to one side, and an earth path with a switch on the other. Now, when the switch is pressed, a current flows to earth through the relay coil. This pulls the large contacts in the relay together. The current then flows to the light through the energized relay. So, with a relay, it's possible to switch a heavy current using a tiny switch only. The only current the switch has to deal with is that needed to energize a small coil in the relay. But remember, by including a relay in the circuit, you've now got this much more to check. The Rover 800's electrical system makes extensive use of relays on all high current circuits, like headlights and horns. The majority of switches are placed on the earth side of the component. Now, I demonstrated the use of a yellow relay on the fog lamp circuit. On the Rover 800, relays are usually either yellow or green. The difference is important. Yellow relays have 4 pins and green have 5. 5-pin relays are used to switch 2 different parts of a circuit. The headlight circuit is a good example. Here, a 5-pin relay is being used to control the main and dip beams. Pin 87A is used for the dip side of the system, and pin 87 is brought into operation when main beam is required. If the 5-pin is replaced with a 4-pin relay, the main beams will still operate, but because there's no pin 87A, the lights won't work in dip beam. So if you do replace a relay, always make sure you use the right one. OK, now we'll translate the theory of fault diagnosis to practice on the Rover Sterling. Let's see how a technician goes about finding a fault on one of the Rover 800's relay-controlled circuits. The fault on this car is that when the light switch is operated, the headlights don't work. So the first thing to do is to check that the fault is there. With the ignition on, the lights won't work in dip, main or flash modes. But dim dip mode, where the headlights come on at reduced power when the side lights are switched on, is working. Before you check the wiring diagram, first refer to the fault diagnosis section in the booklet. This gives a list of the most common faults that could occur on the system in question and could save you a lot of time. Always take this as your first step in isolating the area of the circuit you need to check. We'll be using the new style wiring diagrams throughout this program so that you can become more familiar with them. The headlamp circuit has its own wiring diagram. The feeds are laid out at the top with the earth points at the bottom. There are 3 fuses to check. Fuse 16 in the under-dash fuse box and fuses N and M in the under-bonnet fuse box. But all 3 fuses are shared by the dim-dip system. That's working fine, so they must be okay. Another easy check is whether the lighting relay is energizing. Get someone to switch the headlights on and off while you hold the relay. If you can't hear or feel the relay clicking, it isn't energizing. This one isn't. So that narrows down the fault to either the relay itself or its switching circuit. The relay coil is easy to check using a new fast check relay tester. This particular tester will check 20 or so different types of relay and control unit. Select the correct harness for the type of relay being tested. Then connect the fast check to a power source. The power LED should come on. Press the set button and the 2 zeros shown in the display should flash. Now press the test button. The Test in Progress LED should illuminate. The fast check is now testing the harness you've connected. Plug the relay into the connector on the fast check harness and select the right code number. The code for a green relay is number 1. Early cars, without dim dip, have a yellow 4-pin lighting relay. Now press Set. Then press Test. The Test in Progress LED should be on. When it goes out, the Pass or Fail LED will come on to give you the result of the test. The Pass LED has illuminated, so the lighting relay is okay. That means the fault must be somewhere in the relay's switching circuit. So first, check the feed side of the circuit. With the ignition on, either terminal 85 or 86 in the relay socket should be live. Yes, that's okay. This eliminates the feed side of the switching circuit. The fault must be somewhere in the earth side. From the relay coil, the earth path travels through the headlamp changeover unit to the switch, and from there on to earth. The headlamp changeover unit is like an electronic control unit for the headlights, controlling whether the lights are in main, flash or dip mode. So carry out a continuity check on the earth line from the relay coil to the changeover unit, from the unit to the switch, and then to earth. First, disconnect the battery before switching the multimeter to ohms. This is a good habit to get into because some meters can be damaged if they receive battery voltage. From the relay, a black and slate wire goes to the headlamp changeover unit. A quick continuity check here proves it's okay. From the changeover unit, the wire color changes to blue and black up to the switch, then again to black from the switch to the earth point. With the headlamp switch in the on position, there should be continuity between the blue and black wire from the changeover unit to the earth point at the base of the right-hand A post. And there is. So far, we've checked continuity of the wiring and the switch on the switching circuit earth path, all of which proved to be okay. This leaves one small link we haven't checked, the headlamp changeover unit itself. This is another component that can be checked by the fast check relay tester. Select the correct harness and go through the test in the same way as for the relay. the fail LED has illuminated. So that was the cause of the problem, a faulty headlamp changeover unit. So, following a logical approach to fault diagnosis, this car can be back on the road in a matter of minutes. The whole headlamp circuit is quite complex. It includes 6 filaments, 3 fuses, 2 relays, 2 diodes, a changeover unit, a switch, and a delay timer. But you can narrow the search down to one small area by studying the wiring diagram and planning ahead to find the best area to carry out some simple preliminary checks. As the lighting relay wasn't energizing, there had to be a fault either in the relay or in its switching circuit. The actual path you take will be dictated by the circuit you're working on, but the principles of good fault diagnosis are always the same. Collect all information about the fault. Study the wiring diagram and use your information to isolate the general area of the fault. Work through this area of the circuit in a logical manner until you've pinpointed the fault. Right, so far we've applied the rules of fault diagnosis and found the faulty component with ease. Now we'll see how the rules work out on a different type of system and also look at the part fast check testers play. In this case, the Rover has a fault on the central door locking system. The infrared transmitter won't lock or unlock the doors. So first refer to the fault diagnosis guide. This tells us probably the most obvious thing to check: the batteries in the infrared transmitter. The LEDs lighting up, so they're okay. The next thing is to check the rest of the system. Yes, all the doors function correctly when the key is used. They also operate when the sill button is used. A quick look at the wiring diagram tells us that the system is powered through fuse number 6, but as the rest of the system is working, it can't be that. On this system, that's as far as we need to go at this stage. You can forget the wiring diagram for a minute, because this is one of the circuits on the Rover 800 with its own dedicated fast check tester. Connect the fast check into the system and follow the instructions. It will find the exact area of the fault. This not only saves time, but it means you don't have to work through the wiring diagram at every stage of the procedure. Disconnect the central door locking ECU, then plug the fast check into the system in place of it. The power LED comes on and we're ready to start. We can skip the tests for the lock and unlock because we know that side of the system's okay. So the next test is for the infrared receiver. Point the transmitter LED on the front of the fast check toward the receiver. Press the set button to reset the fast check, then press the infrared test button. The fail LED has come on. Reference to the possible causes tells us that the fault could be in one of 3 places. The easiest test is a visual check on the connectors at the central door locking ECU and the infrared receiver. The connector the fast check plugged into was okay. And the other on the rear of the receiver appears to be all right too. Moving on through the fast check instructions, check the continuity of the 3 wires between the central door locking ECU and the receiver. First, using an ohmmeter, check the continuity of the orange and green wire. One of the probes pushes into the back of the connector. Be careful not to damage the connector when probing the block at the receiver end, because it's very small. And the orange and green wires okay. Now the orange and brown wire. And at the other connector. And we've found it. There's no continuity in this wire. It's easy to locate a fault using a fast check tester. No searching wiring diagrams. The fast check isolates the faulty area and the instructions lead you through simple steps to pinpoint the fault. Regardless of the equipment you use during fault diagnosis, it makes sense to plan ahead to save yourself time. The last problem we'll tackle is a fault in the windscreen wiper circuit. To confirm there is a fault, first check the operation of the wipers in all conditions. Slow speed, nothing. Wash wipe, nothing. Intermittent, again, nothing. Fast speed, yes. Fast speed seems to be working okay. But when the wipers are switched off, they park on screen, not in the proper position. Now it's tempting at this stage to try and cure the fault by replacing the black box, the program control unit. But this could temporarily cure a connection fault in the harness. If so, you've replaced a unit that isn't faulty and left a vehicle with a fault that could recur. Only replace a control unit if you're sure it's faulty. So the next job is to use your information in conjunction with the fault diagnosis guide and the wiring diagram. There are 4 features not working. It's unlikely that there are 2 faults in the system, so you have to find the area of the circuit common to all these features and not to fast speed. The fault can't be in the motor's earth path because both fast and slow speeds share the same one, so you can concentrate on the feed side. The feed comes from just one fuse, number 17. That must be okay because fast speed's working. So that narrows the fault down to somewhere in the motor's slow feed. Follow the motor feed and find the point where it splits into 2, one for the fast speed and one for the slow speed, which incorporates intermittent and wash wipe. The feed splits here at the wiper relay. So the fault can only be in one of 3 places, either in the wiper relay, or the slow feed from the relay to the motor, or the motor itself. So check the relay using the fast check. The code for a green 5-pin relay is 1. And this relay's okay. No fault there. There are only 2 places left where the fault could be. Either in the red and light green wire from the relay to the motor, or the motor itself. Check the wiring first. With the battery disconnected, place one ohmmeter lead on the red and light green wire and the other at the base of the relay. And straight away you see the fault. The connection has pulled out of the relay socket. To prove that this is the fault we're looking for, reconnect the battery and test the circuit. Finally, carry out a full operational check to make sure there aren't any lingering problems. So, we've been through 3 faults on the Rover 800's electrical system. In all 3 cases, you've seen that it's relatively easy to diagnose faults when you follow a logical pattern. In particular, on the wiper circuit, by simply studying the wiring diagrams, armed with information about when and where the fault occurred, we narrowed the faulty area down to one relay, one wire, or the motor, without so much as touching a connection or multimeter. Whether it's an ABS system that's at fault or just a cigar lighter that won't work, a logical and disciplined approach to fault diagnosis will save you both time and money. Always remember to collect all information about the fault. Study the wiring diagram and use your information to isolate the general area of the fault. Work through this area of the circuit in a logical manner until you've pinpointed the fault. It's true to say that most faults are caused by bad connections. Either they become loose, corroded, or damaged, so initial checks here could save valuable time. As I mentioned, components which often are replaced needlessly are ECUs. If you do encounter a problem, don't immediately blame the ECU. That's probably the least likely cause of a fault. Only change one if you've checked every other possible cause. There are 3 new fast check testers which have just been developed to make electrical fault diagnosis even simpler. The first is the relay tester you saw earlier. The second is for in-car entertainment systems, and the third for alternator testing. This one can also be used if you have a battery drain problem. All 3 will help take the guesswork out of fault diagnosis. So, to sum up, watch the previous 2 Service Insight videos on electrics if you haven't already done so. They provide vital information on electrical components, measurements and testing. Use the information in the booklet that comes with this video to familiarise yourself with the electrical fault diagnosis literature and the harness layouts of the Rover 800. And above all, remember that a logical fault diagnosis trail applies as much to the Rover 800 as to any other car. The principles are always the same. No matter how daunting electrics may look, you never have to cope with it all at once. As long as you think in terms of isolating the particular circuit you are working on, the amount of wires you have to deal with at any one time is minimal.